So ICRP recommendations on radon, following from Dominique's discussion on the epidemiology. And what I want to do is go step briefly through each of these publications, going back to publication 65 and what they say about radon dose coefficients and reference levels. So before I do so, I think it's useful just to remind ourselves what we're talking about. So it is inhalation of radon together with radon progeny, and the dose, as Dominique said, delivered very largely by these solid alpha-emitting progeny, 218 polonium, 214 polonium. Depositing in the lung airways and delivering dose to the lungs, small doses from absorption of radionuclides to blood and doses to other tissues, but very largely dose to the lungs. And we can measure concentrations and exposure in terms of the progeny and in terms of the gas. So in terms of the progeny, Dominic was talking, and other people have talked about working levels, which is a measure of the alpha energy in air, and the corresponding SI unit is millijoules per meter cubed. And then if we consider the radon gas, then the familiar unit is becquerels per meter cubed. And then going from that to exposure, it's just a case of including the length of time of exposure. So working level months, millijoule hours per meter cubed, and then for the gas, including the length of the exposure. And the correspondence of the two measurements of the progeny and measurements of the gas is shown here through the equilibrium factor, so the concentration of the progeny relative to the gas. And typical values for F are around 0.4 in most situations in indoor environments, but they can be much lower, as Frank said, in terms of mines where you have high forced ventilation. And the other thing in terms of background is the two ways of calculating dose coefficients from radon. So Dominic was talking about the epidemiological approach to calculate a dose coefficient in which the lifetime risk of lung cancer per unit exposure in working level months is divided by the total detriment for stochastic effects from ICRP publications, so detriment per sievert to give a value of sieverts per working level month. So that's one approach, and the other approach is to use biokinetic and dosimetric models for inhaled radon and progeny, and calculate doses to different tissues and hence a dose coefficient. Okay, so going back then to publication 65, there was an estimate on the basis of the available underground miner data at the time, estimate of lifetime risk of 2.8 times 10 to the minus 4 per working level month, and then using that and the total detriment from publication 60, we derive, or publication 65 derive these values of dose coefficient of either 5 or 4 millisieverts per working level month. And also, on the basis of that, in publication 65, action levels were set in terms of becquerels per meter cubed of inhaled gas, of 200 to 600 for dwellings and 500 to 1,500 for workplaces, on the basis of this equivalence with around 10 millisieverts and this judgment that at that dose the action would almost certainly be warranted to reduce exposures. And the difference between the dwellings and the workplaces is in terms of annual time spent in the different environment. So then moving on to the 2007 recommendations, these same values were repeated. So essentially publication 65 was taken and used to provide the discussion in publication 103. But also in that publication there was mention of the IAEA basic safety standards and their inclusion of this value of 1,000 becquerels per meter cubed as an entry point for consideration of occupational protection requirements. But when the 2007 recommendations were put together, there was a recognition that there was accumulating evidence from the epidemiology and that there was a need to look in more detail at the more recent information. And so a task group was set up at that time and then published this report that Dominic has mentioned, publication 115, which updated the epidemiology from the minor data and also made the comparison with the residential studies. And that publication also included a statement from ICRP to interpret this information. So central to the publication is this update of the estimate of lifetime risk of lung cancer from 2.8 times 10 to the minus 4 per working level month to 5 times 10 to the minus 4 per working level month. And Dominic has explained the rationale and the basis for that change. And on that basis, the upper reference level for homes was reduced by a factor of 2 to 300 becquerels per meter cubed, replacing the previous value of 600 becquerels per meter cubed. And no upper reference level for workplaces was mentioned, only this value as an entry level for consideration of occupational exposure of 1,000 becquerels per meter cubed. So then the next step is publication 126, which provided guidance, radiological protection guidance on protection from radon. And that went further than publication 115 and introduced this range of reference levels, setting a reference level within the band of 100 to 300 becquerels per meter cubed for all indoor environments, so domestic dwellings and workplaces. And then, excuse me, applying a graded approach to exposure in workplaces. So if you be below the reference level, you optimize below the reference level, fine. If the levels of exposure are persistently above the reference level, then a calculation is performed to see if the dose is below 10 millisieverts, still obviously looking at optimization, but if the dose can't be kept below 10 millisieverts, then there is the introduction of requirements for consideration of occupational exposure. So that was the scheme as outlined in publication 126. And that's illustrated here diagrammatically. So the same reference level, 100 to 300 becquerels per meter cubed, set in that range, according to national circumstances, applying to homes and workplaces. And then in terms of homes, there is no requirement for a measure of dose, but in terms of exposures in workplaces, there is this consideration of dose if required because you're above the reference level. And of course, in some workplaces, then there is direct consideration of occupational exposure considered as a planned situation, or in any case, considered as occupational exposure from the outset. Okay, so moving on to new dose coefficients. ICRP at the time of publication 115 made the decision to provide dose coefficients based on dosimetric calculations, as well as obviously being able to calculate dose by the dose conversion methodology. So radon has been for the first time included in the with other radionuclides in consideration and provision of biokinetic and dosimetric models, and it is in publication 137 of this series of reports on occupational intakes of radionuclides, which provides dose coefficients and bioassay data for these sets of elements and their radioisotopes. And in considering dose and calculating it using models, there are a number of factors that affect those dose calculations. Obviously, you're modelling the inhalation of the radon gas and the solid progeny, the deposition in airways, and that deposition obviously depends on the breathing rate, the size and shape of the airways, of course, and the aerosol characteristics, including this proportion of unattached fraction, that is, the progeny that aren't associated with particles in the air. So I'm not going to go into any details of the calculations, but these are results as tabulated in publication 137. So different values, and here I've put them in terms of the SI units, millisieverts per millijoule hour per meter cubed, different values according to the assumptions regarding inhalation and the aerosol characteristics and so on, as shown here. So a range of values from around 3 to around double that for the different circumstances of exposure, and that's about 10 to 20 millisieverts per working level month. Show that again in a second. And you see that value there for indoor workplaces. Whoops, wrong one. Yes, so with a lower breathing rate in workplaces, the higher value is for work in which there is a fair amount of physical activity. But for more sedentary occupations, then the most appropriate value will be more along the lines of 4 or below. So then, if we do the same thing with the dose conversion convention, these are the values we get. And this is almost magically the same value as we get using the dosimetric models. And given all the different assumptions that go into calculating dose using the dosimetric models, and indeed actually this comparison of the epidemiology, it is quite remarkable that we get very similar values. And you can see that they are around double the previous values. So taking into account both the dosimetric calculations and the dose coefficients obtained using the models and the epidemiological comparison, the dose conversion results, what ICRP has recommended specifically for the inhalation of radon 222 and progeny is a single value of dose coefficient for most circumstances of exposure of 3 millisieverts per millijoule hour per meter cubed, or approximately 10 millisieverts per working level month. So that's to be applied in most circumstances. And we have already said, although not yet published values, we've already said that that will apply to exposures, residential exposures of the public in homes, as well as to workers. Now, there is a second value here as well, which takes account of particular circumstances of exposure and higher levels of physical activity, which reflects those higher values that I showed you in those tables. And the report contains a lot of information that enables specific calculations to be done where information is available, say in particular mines where the aerosol characteristics differ from those used in the set calculations that we've provided. So one central value. And yes, and just to say, we are currently working on public dose coefficients, so there will be published public dose coefficients for radon as well as other radionuclides. But this just shows you that there is a very limited effect of age on the dose coefficient. Really because the factors affecting dose tend to counteract each other. So smaller tissue masses give higher doses at younger ages, but lower inhalation rates give lower doses. So the two factors, and there are other factors, but those are the main ones. And yes, just for information then, the 300 becquerels per meter cubed, the upper end of the reference level band recommended in publication 126, corresponds to these doses. So it's 14 millisieverts per year in homes and 4 millisieverts per year in workplaces, just because of the different assumed levels of time spent at work or at home. Okay, so yes, just a word or two about the UNSCEAR review. This shows, which is currently in press, but some of the data, some of the outcome from the review is already available as part of the report to the General Assembly. So this shows the summary of the results they obtained reviewing dose coefficients, so dosimetric methodology, and you can see the ranges there, and our value, the ICRP value of 3 millisieverts per millijoule hour per meter cubed sits centrally within the range of values, as you can see, range of published values. And these are values published using ICRP models, but also other models. So you get a range of different approaches. And then Dominic has already shown this slide, and again, as he's already said, that value, the combined value of 5 times 10 to the minus 4 per working level month is as published by ICRP. So it's central within the range of these estimates of lifetime risk as to be published by UNSCEAR. And if you use that range that was on the right-hand side of that slide and apply the dose conversion convention, then you can see the range in dose coefficients obtained here in millisieverts per working level month. And again, the ICRP value is a central value of 10. So the ICRP conclusions are very much supported by the UNSCEAR review. So yes, that's my last slide. So we have this central revised nominal lifetime risk estimate for lung cancer induction by radon of 5 times 10 to the minus 4 working level month from our own review and supported by UNSCEAR. A dose coefficient of 3 millisieverts per millijoule per hour per meter cubed for use under most circumstances. We do have a higher value, but that can be regarded as a special case for which within the range of values you might get if you're looking at specific calculations that differ from these standard assumptions. And then in terms of control of radon exposures, in the majority of circumstances, that will be using reference levels of 300 becquerels per meter cubed or less. And you see the equivalence in terms of dose. Thank you.
Thank you, John. I mean, we have now a clear overview, a clear picture about the situation with radon. We have 2 questions so far. Maybe there will be others. We have a little bit of time for questions. First one, why does ICRP continue to use working level month rather than just the SE units?
I think, there is widespread familiarity with the working level months. We have used primarily the SI units, so we quote the numbers in SI units, but we give the working level month equivalents so people can use those as well. But actually it's quite a simple conversion one way or the other, so you can easily divide or multiply.
The second question, why was the reference level of the WHO fixed at the lowest end of the reference band recommended by the ICRP?
Okay, so WHO proposed a value of 100 becquerels per meter cubed, but also said that values of up to 300 becquerels per meter cubed could be used if national circumstances would not allow for a value as low as 100. So actually it's not a very different thing that they're saying. Of course, there would always be the expectation, since you are optimizing protection, that if you can set the value at the lower end of the 100 to 300 becquerels per meter cubed, then you would do so. So I think there's no real difference. It's just a slight difference of the way the thing is phrased.
Thank you. Yes, we have a question here. Could you take the microphone, please?
Could you comment on the difference in equilibrium factor for mines compared to indoor workplaces, but not the adoption of an increased equilibrium factor for caves? So there's been a review of caves around the world, and the equilibrium factor is on average about 0.6 rather than 0.4, and the adoption of those equilibrium factors into the dose conversion factor.
Thank you. Yes, I can't at the moment remember what equilibrium factor we used in the calculation for caves, the standard value we used. But of course, it doesn't make any difference to the value you get in terms of working level months. So it only makes a difference when you express the results in terms of becquerels per metre cubed. So in terms of tabulated results in 137, when we're expressing them as millijoules per hour metre cubed or working level month, then the values are independent of that.
Fair enough.
Okay.
Any other question or comment? Yes, please? No? Ah, okay, over there. It's difficult to say. We should have some sort of...
John, in medicine, we sort of started trying to use doses to individual organs where just one organ is exposed. With radon, it's really primarily the lung where the risks are. Would it not be better for us to start, for this particular application, to switch from effective dose to lung dose when conveying the sort of dose-related risk to the public?
Yeah, I mean, you're right, Colin. Of course, I mean, there's a factor of 8 there, just over 8 between. And so when we're calculating the dose to the lung and then basically multiplying by a tissue weighting factor of 0.12 to arrive at the effective dose. I mean, obviously there's a proportionality. But you need to bear in mind that the lung dose is a factor of 8 higher than the doses we're quoting here. Yes.
Okay, it seems no more questions. Thank you once again, John, for your presentation.